All right, so we continue with um, basically waves and wavefronts. So now that we understand that light is an electromagnetic wave, now that we understand that light propagates with, different speeds in different mediums, and let's say it has pretty much same type of properties as any type of wave, right? That means it has a wavelength, it has a frequency. You can use the wavelength and frequency to calculate the speed of the light. Let's kind of, talk about how we can represent then light. How can we represent the light? And technically, there are two models that we're going to be considering. So there is a wave model, and the wave model is basically taking the light and treating it as a wave. So wave model, but there's also a ray model. And so basically, let's say here's a wave, let's say the light is moving as a wave like this, or we can say that light, if you kind of look at it, okay, here's a crest, here's a crest, here's a crest. So you can see right over here, here's a source. Let's say the source generates fields, generates waves, and these waves are propagating like this. So those are the crests. So you can see, right, these are the crests. And those crests are generally propagating, you can see, in this direction or in that direction. It means it's all around it. Now, if I'm using the wave model, then let's say, for example, the wavelength, crest from crest, it's important, the frequency is important, and all of those things. But if I'm considering the ray model, I can say that, for example, here, the wave is kind of generally moving in that direction. And then let's say here is moving in this direction, here is moving in that direction. Well, like this, right? That means I can use a line that is perpendicular to those wave fronts, something like this, that are gives me overall direction. Again, the wave fronts is the locus of the all adjacent points in which all phase of the wave is the same. That means I'm assuming that from crest to crest to crest, right, I can just represent those as wave fronts. Those crests are basically the wave fronts, right? And as they're propagating to the right, I can just use a line that straight line perpendicular to those crests. And you can see, right, if the let's say I'm considering really far away from the source, looking at the source from really far away, those are going to be parallel to one another. So then I can use the, this ray model to better describe things. So as you can see, let's say in the next slide, like here, okay. So you can see, right, very close to the source, those wave fronts are, kind of circular, and my rays kind of more or less follow that trend, right? So you can see, right, the rays also diverging away from the source. So those are, ray diagrams. So I have 1, 2, 3, and giving me like, and now you can see, right, there are, many more that I can do. And from very close to the source, those rays are diverging away. If you consider then a really far away, that means you're considering, let's say, the source to be really far away, then those waves can technically be moving such that, so let me kind of show you what I mean. So let's say here's a source. See that kind of like a circular, but as you go far away, then they can kind of become like, parallel like that. And then my rays will be parallel to one another as well. So these are known as plane waves. That means I can kind of consider this as like a plane like this, or a plane like that, right? Or a plane like that. And any type of waves or rays coming out of that, they're going to be all parallel to one another. This becomes, useful when we're going to consider things like mirrors and lenses, because it's difficult to use a wave model of light to describe those phenomena. But using the ray model is very, easy and straightforward. So for example, here we have a window. So there's a window glass, right? And there are some, several things happening. So let's say we have a hat. So what I have here is, for example, there's a hat, and you can see, for example, the woman here outside, she can see the hat directly if she looks at the hat directly like that, because the light from the hat goes, let's say, and reach her eye. But she can also see the hat to the reflection of the window glass, right? See the light from the hat moving like this. So those are the wave fronts. So moves like this, hits the surface of the air window, let's say boundary, right? Hits the surface, and then it's reflected back. And it's reflected back, woman can see then the image of the head generated behind it. Okay, so this is then reflected, image. Okay, so that means there's now two, hats, one outside, one inside, but one is the actual hat, the other one is the image of the hat. Well, the light from the hat can also then propagate into the window and to the other side, and the person here can see that. Okay, so the person can see the hat, but person doesn't see this guy here. Person see the, image that is, of the hat that is outside. That means there are a lot of things going on over there. And to describe all this, ray model of light is much, much simpler. So that means the next two chapters we're going to use the ray model to describe things. So in this chapter, we're going to talk about reflection, refraction. In the next chapter, we're going to then talk about when the light is reflected off of a mirror, or when it is refracted into the lens and things like that. So that means we're going to be using a ray model of light to understand all this phenomena. All right, so let's first kind of see what's going on. We will consider the light that is moving in medium A. So let's say this is air, right? So A is the, our first medium. Let's say in this case it's air. So the light coming, maybe like the sunlight, right, from far away. So then you can treat those lights as rays that are parallel to one another. So then they reach a boundary between, two mediums. So this is air. So let's say, and this is, let's say glass. Okay. So then what you have here is when the light is incident, so we call it incident, right? So this is the incident, right? So when it's incident to the surface, okay, so you get two things. Some of the light can be then reflected back into medium A. Sometimes it could be the 100% of the light is reflected back. Sometimes maybe 20% reflected, and then 80% maybe refracted. Again, I'm just shooting some numbers, but the idea here is that there will always be a reflection. Is it going to be the entire light reflected or fraction of it reflected? But there will always be some reflection. Then some of the light will refract. Refract means that it transmitted to the other side. So then the light refracted to the other side will exhibit some very unique let's say properties that we're going to see. One thing you're going to see right now, you can see right now from the picture, is that it actually changes direction, right? So see, this is the incident, but instead of going like that, it actually goes like this. So there's a changing direction, but there's also another thing, which is changing speed. And you can see, right, those things is a little bit easier, especially changing direction, right? It's easier to do, demonstrate using the ray model of light. So that's why we will be using that, okay? So we're gonna try to understand what's going on when the light is reflected, what's going on when the light is, let's say, propagating to the other side, and use those things to, then solve, physics problems. All right, so let's again assume that the light here is in medium A, right? Moving from a source that is far away. So that again, when you have the incident rays, and there's those, 1, 2, 3, those are incident rays, right? If they are parallel to one another, that means the source is really far away. Okay, so now they move in and they hit the surface. Okay, so now let's say this surface, which is B, we don't care about if the light goes into the other side at all. So right now we're only looking at the, let's say, reflection. So what happens here is this: the light reflects back. You can see, right? Ray 1 hits the surface, reflects back. Ray 2 hits the surface, reflects back. Ray 3 hits the surface, reflects back. You can see, right? Rays 1, 2, 3 parallel to one another before the reflection, and rays 1, 2, 3 parallel to one another after they are reflected. So this is known as a specular reflection. That means the surface is very smooth. So when the rays are reflected, all of those rays are parallel after the reflection as well. Compare that to the diffuse reflection, where we can see, right, 1, 2, 3 are parallel to one another, and then 1, 2, 3 are just going in a random direction after they're reflected. So this is known as a diffuse reflection, and that's because the surface is not smooth. You see there are a lot of bumps and imperfections and things like that. So that kind of diffuses the light a little bit. All right, so what we have here is, let's say you have A as specular reflection, B as a diffuse reflection. So those are kind of like two extremes. Most of the time is maybe somewhere in between, but for us, you can see that it would be much, much easier to understand all this if we consider a specular reflection. And this is what we're going to be doing. So that means we're always going to be using specular reflection, because let's say if I'm using a mirror, well, mirror has a very smooth surface. If I'm using a lens, lens has a very smooth surface. That means we can then use lens and the mirror, right, to demonstrate that as a specular reflection. All right, so now let's see what's going on. So again, we have now two mediums, right? Medium A, medium B. So now you have incident ray moving and hitting the surface at that position, right? Now what we do here is kind of like before, looking at this thing like this. So here's, let's say, the surface. Here's medium A, here's medium B. So let's say when the light strikes the surface at that position, so what we do here is we draw a normal line to that position. So let's say here's a normal. That means it's a line that is perpendicular, right, to the surface. Okay, so right, this is this normal line over here. Because then I'm going to take the direction of the incident ray, incoming ray, with respect to the normal, not the surface, but with respect to the normal. I'm going to say this guy here, right, starting from the normal line to that ray. So this is going to be then theta A, which is the angle of incidence. Okay, so this is angle of incidence. Well, the angle of incidence represents, what is the direction of the incident ray relative to the normal. As I said, right, some of that light will always reflect back. Now here's when it reflects back, it's going to go reflect like this. Every time you measure the reflected light, what you will see here is that reflected light, again measured with respect to the normal, let's say theta r, right, will always be equal to the incident angle. And this is known as a law of reflection. That means angle of reflection measured from normal is equal to the angle of incidence measured from normal. They will always be the same no matter what. Every time some of the light is reflected, they're going to be the same. So that's why. Let's jump back to the previous slide. See here, if I do the normal like that, those two are the same. Normal like that, those two are the same. Normal like that, those two are the same. Even here, see, this is the normal. Those two are the same. This is the normal. Those two are the same. And here, this is the normal. Those two are the same. That means when it reflects, it always reflects with the same angle as the incident angle. All right, so this is known as a law of reflection. Now, another thing happens is that the light propagates to the other side. And you can see, right, then the direction is slightly different. Okay, direction is slightly different. That means there are two things, happens when the light goes from one medium to another, and those mediums basically have different density, you can think like this. So, and what happens here? It changes direction. And also changes speed. Okay, two things that are very important to understand. It changes direction when it goes into more dense material, or when it goes from more dense to less dense material. So it changes direction, also changes speed. So remember, if I take this air, then velocity is same as speed of light in vacuum, right? So the velocity of the air is basically the c. When it goes into the, let's say, medium B, and let's say, for example, this is glass, right? So this is velocity of air, so then the velocity of glass. Well, this is already will not be equals to c. It will not be equals to c. It's going to be less than c. It's going to slow down because it's more dense So there are more collisions and things like that, more absorption, scattering, and let's say, re-emission. So the light will slow down. Plus it changes the direction, okay? Now, to understand kind of like how to incorporate these two, we can then, let's say, represent the direction of the refracted ray. Refracted means the propagated, right? Transmitted ray with respect to, again, the normal. So I can measure this theta B. You can see, right, this is theta B, and I can already see that theta B is not equals to theta A. That means you have those two things. So direction of B is not same as direction of A, and velocity of B is not equals to velocity of A if those mediums are different. All right. So to understand how are they different, is B bigger than A, or is it less than A, or is it always bigger or always less, or same thing with speed, we can look at what we call index of refractions. Again, we kind of talked about this index of refraction. So one thing I have here is if I take index of refraction of medium A, so this will be C divided by VA. That's the equation for the index of refraction. Okay. So again, this name index of refraction. So don't think that this is only for the refracted medium. It's just the name is like that. So it's just a this index of refraction represents the ratio of the speed of light in vacuum. So that means this is a constant that never changes, divided by speed of light in this material, in this medium. That means what I have here is this is for air, as I said, right? So then I can say this is C, and because it's it's almost C in air, so then I can say is 1.00. That's the index of refraction for air. Then if I go to the medium B and I say this is C over VB, then I'm going to get a different number because VB is not equals to VA already. And since VA is equals to C, VB has to be less than C because, nothing can go faster than speed of light in vacuum. Now here's what I have. So if I'm calculating this, I'm going to get 1.5 roughly. That's for glass. That means my index of refraction for medium B is 1.5. Then sometimes we can just easily use or simply use the index of refraction to represent type of medium. Because if I say NA is equals to 1 and NB is equals to 1.5, you right away know that medium A is air, medium B is glass. So when I, for example, have here, NA equals 1, NB is equals to, for example, 1.33, then this is air and this is water, because this is index of refraction for water, right? So I have a table where, some of those values you guys can see, but, more or less know the air, make sure you know the index of refraction for air, index of refraction for glass, and index of refraction for, let's say, water. So air is 1, glass is 1.5, and water is 1.33. Okay, so now here's then what we have. So we're going to look at sort of like, let's say, what's going on with the light when it goes from, one for a medium with one index of refraction to medium with different index of refraction. Okay, so here we can see that the light bends toward the normal, but is this always the case? Does it, is the index of refraction, if you switch the index of refractions, right, going from more, dense to less dense, will that still be, deflecting toward the normal? All right, so we're gonna see this in the next few slides, and hopefully, you will understand what's going on to the light in terms of its direction, depending on the, the direction of the propagation in terms of from lower index of refraction to a higher index of refraction, or from going, let's say, from high index of refraction to lower. So let's say if the light is incident like this, what will happen to this light? All right, so let's dive into that. Okay, so one thing I want to mention before that is that one equation that kind of allows us to do all this type of calculation for not just observation but calculation is known as a law of refraction, and it was developed by the you can say Willibord Snell. Actually, it was not Snellius, but he's a Willibord Snell. You can see right in 1591 to 1626. So this equation is like roughly 500 years old. So he concluded that index of refraction, so index of refraction of medium A times sine of theta A equals then index of refraction of medium B times sine of angle B. That means he's not relating index of refraction and angle of incident and refracted, but the sine of the angles, right? So that means what you have here is this. So if I kind of rearrange, right, and sine of theta A divided by sine of theta B, if I kind of divide both sides by sine, and then you will see then divide both sides by NA, then I'm going to get this ratio. That means ratio of the index of refractions NB over NA related to the ratio of the sine of the angles, sine of theta A over sine of theta B. Here's one thing we can also talk about. Remember that index of refraction is equals to C over V. So let's say for NA is C over VA, and for NB is C over VB. All right, so then how about if I'm doing index of refraction B divided by index of refraction A? What if I'm using this ratio? Well, here's what I get. See, NB is C over VB, and A is C over VA. Well, C is going to cancel out, and this ratio of NB over NA gives me VA over VB. That means this ratio is equal to the ratio of the velocities, but NB over NA equals VA over VB. That means I can come back and rewrite that, the sine of theta A over sine of theta B, which is equals to NB over NA, it's also equals to then VA over VB. Excuse me. That means the Snell's law can also be written in terms of those things. So if I then rearrange, I get, modified Snell's law equation of VB times sine of theta A equals VA times sine of theta B. All right, so they are equivalent, okay? Because, whatever I use this equation for and I use the other equation, I'm going to get exactly the same answers. But the one is in terms of index of refraction, the other one in terms of velocities, right? So they still represent kind of like same thing. And obviously you can see, right, that this ratio can also be useful in some cases. All right, so let's see then what we can have. Let's call this case one. So case one is this. So we are going from NA, medium A, into medium B, but NA is less than NB. That means we're going from less dense to more dense, okay? And what we want to know, what will happen to the refracted light, okay? So one thing we get here is this. So this is that case one, where you go, or you can say NB is greater than A, it doesn't matter, right? So, and NA is less than NB, or NB is greater than A. So what we get is this. As incident light is the surface, this is being the angle of incident, light will always refract such a way that angle that it makes with the normal, let's say this theta B, will always be less than theta A, would always be less than theta A. It means it will bend toward the normal. So you can write this is like original path. So it deviates from original path, it bends toward the normal. Also then what we get here is because index of refraction of B is greater than index of refraction of A, then velocity of B has to be less than velocity of A. Okay, that means for case one, you basically get that. For the case where the medium B, taking the second medium, right? So medium B has a higher index of refraction than medium A or material A, then the light will bend toward the normal and it will slow down, okay? So that's why, you have then theta B, which is less than theta A, and VB, which is less than VA, okay? So you get that. All right, so what happens when it's other way around? So let's say a case where, let's say case two, where then NB is, less than NA. That means the medium A, right, now is more dense, okay? Medium A is now more dense. And that means, let's say, for example, it goes from glass to air or from glass to water, right? So what happens here is, so this is being, let's say, the original path of the light. All right, so let me try to like, here's the original path of the light. So if you then comparing the refracted angle, right, angle of refraction to the incident angle, theta A, this time theta B is greater than theta A, all right? That means as light goes from higher index of refraction to lower index of refraction, it bends away and it also speeds up, okay? So it's gonna then move faster than in medium A and bend away from the normal, okay? So this is case A. That will always, when the light goes from glass into air, it right away picks up the same speed as it had before, you know, in vacuum. So it's gonna right away move at the speed of, all right, so then what is case 3? Well, case 3, if the light coming perpendicular to the surface or along that normal line. Well, in that case, theta A is 0. That means sine of theta A is 0. That means theta B is also 0. And what happens here is the light is incident and some will refract without changing direction, right? Without changing direction, and some will reflect it in a opposite direction. That means there is no change in direction. Okay, in this case, there is no change in direction for the light. Okay, now how about velocities? Does it mean velocities also are constant? No, of course not. You still go into a more dense medium or material, you're gonna slow down. That means if you still have to kind of look at it in terms of that. Remember, NB over NA is still equals to VA over VB. Even though thetas are 0, NB and NA are not 0, right? So then you can still use this to figure out what will happen to the velocities. If NB and NA are not the same, V and VB cannot be the same as well, right? So you can see it like this. So let's say if you have VB, so VB is equals to, let's say, NA over NB times VA. So you can see, right? Only when NA and NB are the same, VB and VA will be the same. But every time they're different, you have a different speed. No deflection, right? But speed still changes. All right, so that's why you see something like this, or when you put your straw into the glass of water, you see similar thing, right? So the light seems like entering the glass, and then it seems like it's broken or something like that. Well, it's not broken. It's just the light changes direction, right? When then the light coming out from water. So let's say what you have here is what you see over there is the light that starts from water and comes out into the air. Remember, when it comes out into the air, it bends away from the normal. So you see the image is generated by that, let's say light, right? The light that bends away from the normal. So your image, the image that you see is the one that actually generated, okay? Generated by that, let's say ruler. So here's one more way of looking at it. So think like this. So let's say that's the ruler, right, in water. See, let's say if you're looking at the bottom, right? So it comes in like this, and then see, this is the normal, right? So it bends away from the normal. Or another one here like that, it bends away from the normal. But what you see here is, well, you see that you see this refracted light, right? So these are the refracted ones. You see those refracted lights. The image of this bottom of the ruler is generated for your eye by those refracted light. And what you do, you trace them back inside, and then they appear right there. That means you see the bottom of the ruler to be actually right there, which is the end of the ruler, which seems like the ruler kind of bends, it's kind of broken like that. Okay, nothing wrong with the ruler, it's just the image that it generates for you because you're outside of water, right? See, if you're here, if you're looking from here, right, then what you see here is that nothing wrong with this, but this guy will be, let's say, different, okay? But, let's say you see kind of like two different things depending on which medium you are. All right, so this is the index of refraction for let's say some wavelength here, 589 nanometers, which is roughly a greenish yellowish color. So we have water, 1.33. Okay, so a lot of times we just use 1.33, but let's say C for ice is 1.3. So sometimes we just use 1.3 for water in general, and that's fine. But if you specifically know it's water in liquid form, then you can just use 1.33 to be more accurate. Okay. So you can see, right, one thing we have here is you have like a, glycerin, crown glass. So the glasses, I mean, like about 1.5 roughly. There are different type of, acrylic glass and things like that, crown glass. So you might have slightly different values. Generally ranges from 1.5 to 1.55, let's say. Rock salt, quartz, diamond, and so on and so forth. That means depending on what we have here, right? So the index of refraction increasing means it's more and more dense material. Okay. But the question here is this. Okay, so why does the light slow down when it goes to more medium, let's say dense medium? Well, okay, so think like this. So here's a wave, and let's say this is the wavelength. So let's say this is the original wave. And let's say this is air or vacuum. For us, is the same, right? And let's say here's the coming here, and then there's a medium surface between two mediums. So this is A, this is B. That means the light that is propagating like this hits surface. That means it's going to go to the other side. So now, if NB is greater than NA, for example, then the light that goes to the other side has this shape. You guys see the difference? The wavelengths are different. That means the wavelength here, lambda n, let's say, right, is different. It's shorter. And this happens if the NB is greater than NA. And it will be other around. So let's say if the light comes like this from here and then goes to the other side, then it will pick up and be a greater, a wavelength. That means the wavelength of the light changes as it goes from one medium to another. And one thing I can do, then I can calculate this wavelength by taking then the wavelength in vacuum divided by the index of refraction. So that you can calculate, right? So let's say you have a light that is 500 nanometers. What will be 500 nanometers, right? So this is 500 nanometers in vacuum. So what will be this if it enters, let's say, a glass, which has a, 1.5, right, index of refraction. So then if I have that, for example, 500 divided by 1.5, then we get 333 nanometers. That means the wavelength decreases. Now, can we see this wavelength? 333 nanometers, 333. We cannot, remember. So this is actually below our, visible range. But obviously we can see things inside the glass, right? So if you put something inside the glass, in a glass of water or something like that, right, we can still see the colors and everything. So how come is that? Well, because frequency doesn't change. So the frequency of a wave does not change when passing from one material to another. And our eyes interpret frequency, not the wavelength, to generate the colors. So for us, if the frequency doesn't change, whatever frequency of 500 nanometer has in vacuum is the same thing in glass, same thing in water. So that's why we can see it. Same, you take an object which is blue, in air it's blue, you put it in water, do you see it as red? Of course not. You still see it as blue because it's the same color, because of the same frequency. So that means this is what we have. That's why, so since V is equals to wavelength times frequency, see if this wavelength changes, so does the velocity. That's why, for example, here, because wavelength, let's say of B is less than wavelength of A, medium A, right? That's why velocity of B is less than velocity of A because of the wavelength change. Okay, so that's kind of what we end up understanding, hopefully, in terms of this. All right, so we're ready to do some examples. So what we have here is the vitreous humor, which is a transparent gelatinous fluid that fills most of the eyeball, has an index of refraction of 1.34. Visible light ranges in wavelength from 380 nanometers violet to 750 nanometers red as measured in air. This light travels through the vitreous humor and strikes the rods and cones at the surface of the retina. what are the ranges of wavelength, frequency, and the speed of light just as it approaches the retina within vitreous humor. All right, so I guess, you know, sort of like a thing like this. So if this is your eye, right? So that's basically the retina right there. And what you have here, your eye is kind of actually the lens, and then inside is that fluid. Okay, so when the light comes in, then it moves toward the, let's say, your retina. So it actually has to go through that, let's say, through that fluid. Okay, so that fluid has the index of refraction of 1.34. Okay, that means what we have here is we have the wavelength original is 380 nanometers. Or let me do it like this. So this is then going to be for the violet, and this is going to be for the red, 750 nanometers. And I'm going to use prime to indicate those values inside the vitreous humor. All right, so what I do here is this, right? So WV prime, then, wavelength V prime, not W. So is equals to then wavelength in vacuum divided by index of refraction. That means 380 nanometers over 1.34. All right, so if I do this and then I do the calculation, what I will get here is 284 nanometers. And obviously we could not see this technically, but again, remember the frequency doesn't change. So lambda red prime is then lambda, well, this is lambda V, right? And this is lambda red over N. So this is 750 nanometers over 1.34. And if I do this calculation, I'm going to get 560 nanometers. All right. So what is then the frequency? Well, frequency, I can use this. Frequency of violet is then wavelength of violet, speed of light divided by wavelength. So if I plug in, right, 3 times 10 to the 8 over 380, what I will get here is 4 times 10 to the 14 hertz. Same thing if I do frequency. So this is already part B. This is part A. So frequency of red is, again, C over wavelength red. Plug in the values, we get 7.89 times 10 to the 14 hertz. Higher frequency, as you can imagine. Well, this is also then equals to F prime red, because it doesn't change, and F violet red. F prime, right? That means the frequencies before and after is still exactly the same. All right, part C says, what is the speed of the light just as it approaches the retina within the vitreous humor? Well, I know that index of refraction equals speed of light in vacuum over speed of light in that material medium. So then I can use this V, which is going to be then C over N. That means 3 times 10 to the 8 divided by 1.34. Then I can calculate what is the velocity. And it is 2.24 times 10 to the 8 meter per second. That means the velocity of the light is less in the vitreous humor than in vacuum. But it's very fast still, but you can see, right, it's a big drop, okay? All right, so now what I have here is then another example. It says a light traveling in air is incident on the surface of a block of plastic at an angle of 62.7 degrees to the normal, and is bent so it makes 48.1 angle with a normal in the plastic. Find the speed of light in plastic. All right, so what I'm given is theta A, 62.7 degrees, theta B, 48.1 degrees, and I'm given that medium A is air, that means NA is 1, and I want to find VB, and I know that VA is equals to also C. Those are the information I'm given. All right, so you can do like a rough picture. So here's a picture. So the light is incident like this. So then this is 62.7. Then because we know that the medium A is air, and medium B, we don't know what it is, but it has to be more dense because light, as it enters, right, refracts, has a smaller angle of, refraction. That means here's then this is theta B, which is 48.1, as you can see, right? Now, one thing I can do here is, I know then, let's say for this VB, I can solve for VB in terms of then C over N, like in the previous example. So all I have to do here is to find this NB, then I can, plug it into this equation. And I can do that because Snell's law, NA sine of theta A equals NB sine of theta B. I can use this equation to solve for NB, which is NA sine of theta A over sine of theta B. So it's 1 times sine of 62.7 over sine of 48.1. We calculate index of refraction of this medium to be 1.194. Then I can come back here and say, all right, so 3 times 10 to the 8 meter per second divided by 1.194, and I will get 2.51 times 10 to the 8 meter per second. And that's going to be then the velocity of the light in this medium, which is a plastic. So the plastic has roughly that index of refraction. Alternatively, we can do this equation, modified equation of the Snell's law to use this, remember? So VB sine of theta A equals VA sine of theta B. Remember, I can use this equation because I know VA is C sine of theta B. Then I could have just calculated VB from here, right? C times sine of theta B over sine of theta A, and we would have the same value. So either one is a right approach to solve for this. Maybe this one is a little bit easier, second one, but sometimes problems ask you two things. So let's say maybe ask you for find index of refraction as well. So you might as well would have gone, let's say, the first method. But second method is equally correct. All right. Here's then another example where we have, let's say, a layer of water covers a slab of material X in a beaker. So a ray of light traveling upward follows the path indicated. Using the information on the figure, find the index of refraction of material X and then the angle the light makes with the normal. All right, so we're gonna have to solve this problem in a minute. All right, so back. So I need to give myself a little more room here. All right, so again, what we have here, we have like 3 mediums now. So some medium X, here is water. And remember, that means I can say that, so what I can do here is like, let's say I can say this is N1, this is N2, and this is N3. Instead of A, B, you can just use 1, 2, and 3 like that. So then medium 1 is unknown medium, right? We don't know what that material is. Second material is water. Third one is air. Okay, that means light gonna here come out into the air, but we don't know. Is it gonna bend toward the normal, away from normal? Well, hopefully you know now, but let's say we don't know at this instant. Okay, so let's solve for for part A, which is what is the index of refraction of medium X. Now, because the water medium 2 is 1.33, and because we're given what type of material it is, we assume that we know the its index of refraction. So I'm looking at this, N1, N2 surface. So N2 is 1.33, and 1 is, unknown. But then what I'm given here with respect to the normal, so here's the light incident one, right? And it goes like this. So I'm given this is as 48 degrees, and we're given that this is as 65 degrees. Now, so when I write what's given to me, then I can say then, now let's use this. This is then theta 1 instead of theta A. So let's say theta 1. Now, what is theta 1? That's 65 degrees. You have to be careful. Remember, theta is with respect to the normal. That means it's not 65. If you thought it's 65, that was wrong. It's actually 25 degrees because this is incident angle, right? This is, let's say, what we would call theta 1. What is then theta 2, which is a refracted angle? Well, it is with respect to the normal, so it is 48 degrees. Okay, so then what we have here is, we're also given then N2 here is 1.33. And let's say if I want to find, N1, I already have enough information to plug in into the Snell's law. Again, replacing A's with 1, B's with 2. So N1 sine of theta 1 equals N2 sine of theta 2. All right. Then from here, it will be simple enough for me to solve for N1, which will be N2 sine of theta 2 over sine of theta 1. So N1 is equals to 1.23 sine of then 48 degrees divided by then sine of 25 degrees. Let's see what N1 is. And here you can predict what type of index of refraction should we have. See, theta 1 is less than theta 2. That means light, as it goes from this unknown material into the water, it bends away from the normal. This means N1 should be greater than N2. You should predict this. And we do get that. So we get 2.34 for the index of refraction for this material. All right, so that's part A. Part B here is then, all right, so then after the light goes from water into the air, it's going to refract again. This being the normal, in which direction will it be then bending? Okay, that means I'm taking now, going from N2 to N3, where N2 is my initial one, N3 is my final one. So then what I have here is then I have N3 sine of theta 3, is equal to then N2 sine of theta 2. It doesn't matter in which order you write this equation, right? Now, what is N2? Well, N2 is 1.33. How about N3? Well, N3 is 1 because it's air. If you want 1 or 1.00, same thing, right? Well, what is theta 2? Well, so this is theta, this was theta 2, right? For the, let's say, for the first surface. But since, see, those lines are parallel to one another, that means this is also 48, right? That means I can use this equation, right? Where then I have then, okay, theta 2 is 48 degrees as given. So you can see, right, I'm pretty much given everything that I need to calculate theta 2. Theta 3. All right, so then I do sine of theta 3 equals N2 over N3 sine of theta 2. So, and then, which is basically, N2 here is 1.33 over 1, then times sine of 48 degrees. Then what I do here is I take inverse sine to solve, which is going to be then 1.33 times sine of 48 degrees. And you should expect the light to bend away from the normal. So then theta 3 should be greater than theta 2. And we end up getting that because this guy here is 82 degrees because it bends away from the normal. All right, so hopefully you guys able to see all this going on in this, let's say with the Snell's law, with this index of refraction, how it allows you to be able to calculate, right, all of these things. Let's now go into a special case for the this type of interaction. This happens only if you're considering, remember this case 2, where NB is less than NA. That means we go from more dense to less dense, higher index of refraction to lower index of refraction. Only in this case it will work. The idea here is this, so let me kind of do it here. See, let's say, here's your incident. This is your theta A, then this will be theta B. Remember, because it will bend away from the normal, and theta B is always greater than theta A. That's, the idea for this type of thing. Now, if I continue increasing this, I'm going to increase theta B. And then at some specific theta A, let me use different cells, some specific theta A, the theta B will bend so much that it will be parallel to the surface. That means it will be perpendicular to the surface. So then we call this critical theta, critical angle. That means what I have here is, you can see right here is ray 3. Ray 3 is the critical angle because ray, coming out of, the refracted is perpendicular to the normal. Now, what happens if I increase my incident angle more than critical angle? Then all the light is reflected back. That's why it's known as a total internal reflection. Everything is reflected back. Again, it only happens when you are going from more thans to less thans. That means this NB less than NA is the requirement for that. All right, so then what I have here is this. If I'm writing then NA sine of theta critical equals NB sine of, when theta A is theta critical, theta B is 90 degrees, which is basically 1, right? Becomes NB. Then divide both sides by the NA and you end up with that equation. So you can calculate what is the critical angle for, let's say, water-air, let's say a combination, or glass-air combination, or glass-water combination, or water-oil combination, and things like that, right? So again, this is known as a critical angle. And after any direction of the incident beyond critical angle, see, completely reflected back. That's why it's known as a total internal reflection. All right, so let's look at an example to understand this total internal reflection. So the critical angle for the total internal reflection at the liquid-air interface is 42.5 degrees. If a ray of light traveling in the liquid has an angle of incident at the interface of 35 degrees, what angle does the refracted ray in air make with the normal? Right. So we are given right away that we're dealing with Na, which is some kind of, a liquid, not water, some kind of liquid. So we don't know what it is, right? But then Nb here is air. Okay, so some kind of liquid air combination. But what we're given here is this. When the light is incident in water, in this liquid, such that it makes this critical angle, remember, this means that the light is perpendicular in the other side, right? Then this critical angle for this combination is 42.5 degrees. All right, so what can we do with that information? Well, I can use the equation in the previous slide, where then sine of theta critical equals then, NB over NA, right? I can use that to calculate it. All right, so I can use it to calculate it. Okay. That means I can calculate NA, which is then going to be NB over sine of theta critical. NB is 1, then sine of 42.5 degrees. Then what I will get for the index of refraction for this liquid is 1.48. All right, 1.48 for this liquid. All right, now that's one important information that I have. Then for part A, I'm told, okay, so then let's have another light in this medium A, which is now has index of refraction 1.48, and it's going out into the air. Now let's say that this light, instead of critical angle, has 35 degrees, well below critical, so light will refract into the air. What will be that refracted angle? Now it's simple, that because I can do NA sine theta A equals NB sine of theta B, and so forth theta B. Since sine of theta B here is equals to NA over NB sine of theta A, and then use the inverse sign. Where I get NA over NB times sine of theta A, all of them in the argument, right? All of them in the argument. So if I calculate for this theta, plug in, let's say, for NA, it's 1.48. For NB is 1. and then the theta B, theta A is then sine of 35. Okay. So if I calculate, you should expect theta B to be greater than theta A, and we do get that, 58.1 degrees. All right. Part B says if a ray of light traveling in air has an angle of incidence at the surface of 35 degrees, what angle does the refracted ray in the liquid make with the normal? That means we are kind of looking at other way around. So can I clear this so I have room to work with? Okay. So that means we are looking at this combination, right? So here's the normal. So light is coming from air with 35 degrees. That means NA is now 1, theta A is 35, and then it's going to go into NB, which is 1.48. Now, because we know that it's going to then bend toward the normal, it's going to be something like this. So this is theta B, and I can, expect that to be a smaller number. Again, what I do here is I plug in this NA sine of theta A equals NB sine of theta B to calculate this, and we should get then theta B to be 22.8 degrees. Right, so I have a more complete, breakdown in the slide if you want to go back and look at it. But basically the same thing as I did over here to solve for that. Remember, here I was solving for theta B, and same thing I do here and solve for theta B and get 22.8 degree, because in this case, NA is 1 and NB is 1.48, so the ratios are slightly different over there. All right. The last concept in this chapter is the polarization. And this is kind of looking at the light, not necessarily particle or ray or wave or thing like that, but understanding that electromagnetic wave is a combination of electric and magnetic fields. But for example, if I just think of the light, as, let's say, electric field, but let's say here's a source, and it generates electric field in this direction and in that direction, an electric field in this direction, in that direction. That means the light that is generated by this source has every single direction. It means it's basically like this or like that, right? And it generates the light in very specific direction the whole time. Every time it generates a light with a different direction. And it does this so quickly that when you look at it, it seems like it's a uniform in every direction light generated by this source. So this is known as a natural or unpolarized light. Basically this guy over there. So it's a natural or unpolarized light. That means sun generates natural or unpolarized light. Light bulb generates natural unpolarized light. That means the way they generate light is in kind of like in every single direction. Okay, that means you can't just say, okay, it's either vertical or just horizontal or just this, right? It generates in every single direction, as a function of time. So that's why we call it natural or unpolarized light. But one thing we can do, we can polarize it. So what does it mean, polarizing the light? Well, think like this: as the light is moving like in this direction, we can assume this. So instead of like thinking that in every single direction, so let's simplify and say, okay, so we have two major directions, vertical and horizontal. Okay, vertical and horizontal. That means it has all the direction superimposed into vertical and horizontal. And it is moving with this velocity, on the x-axis, let's say. What we can do here is we can put a device, some kind of polarizer. And polarizer can be different shapes. So let's put like let's say circular. Every polarizer has polarizing axes. That means inside the polarizer, there are axes over there that has special, liquids and, things like that can absorb the light. So let's say for my polarizer, the axes that I have, let's say, are vertical. Okay. Now what happens here as the light, think like this light over here, right, is moving toward the polarizer, it will go through the polarizer. But when it goes through the polarizer, polarizer absorbs everything that is perpendicular to its polarizing axis. Again, those lines, right, are polarizing axis. Any light that is perpendicular to the polarizing axis will be blocked. Anything that is parallel to the polarizing axis will be transmitted. That means the light that comes out of this other side will have only one direction that matches the axis of the polarizer. That means this light will be vertical, just like the polarizing axis. And this is known as polarization of light, because this light has only one direction, vertical. Okay, so what if, let's say, the polarizing axis was horizontal? Then the light that comes out would have been horizontal. That's about it. Now, what can we do with this? Well, what we can do with this is that, let's say as the light is moving with, now polarized light is moving, I can put the second polarizer. And now think like this, second polarizer has what? It has axis. Let's say now the axes are like this, which are horizontal. So as this vertically polarized light enters the horizontal axis, or the polarizer with horizontal axis, well, polarizer blocks everything that is perpendicular to its axis. That means what you have here is no light. That means if you look into this polarizer, you see no light, because you can rotate it and have its axis to be perpendicular to the, polarized light, and then you can then completely block the light. All right. So that's the idea. That means you have two polarizers, right? So this one here is polarizer. And generally the second one is known as an analyzer. Okay, second one is known as an analyzer. And you cannot block a natural light with a single polarizer, but you can polarize the light with the first polarizer and then block it with the analyzer, second polarizer, okay? Now what happens here is then, we're gonna talk about, let's say, when you have the light going through the polarizing, let's say when it goes to the polarizer, so let's see, right? So the light for most sources, such as light bulbs in a random mixture of waves, linearly polarized in all possible transverse direction. Such light is unpolarized or natural light. A Polaroid polarizing filter can convert unpolarized light to linearly polarized light. Okay, and this is basically what I was kind of talking about. So here's natural light going to the polarizer, and then what I have here, polarizer, depending on its, let's say, axis, right? It can then, block it, polarize it. And then when the light here is polarized, okay, that means the light that comes out of the polarizer will have the same direction as the polarizer, or the axis in the polarizer. And then you can use the analyzer to either completely block it, or maybe, polarize it even more. That means, the idea here is that you're decreasing the intensity. So for example, when the light goes from here and goes to the first polarizer, so let's say this is taking the intensity of the light. Remember, intensity is energy, right? Per unit time, or power per unit time. As it goes to the first polarizer, the intensity, let's call this 0.1 over there, right? Intensity of 0.1 is always exactly half of the intensity before. That means with one polarizer, you can drop the intensity of unpolarized light exactly by half, by 50%. Okay, remember that's because, you can superimpose as a horizontal and vertical. And when it goes to the polarizer, one of them is blocked. That means you just have other one, which means a half of the intensity. You can think like half the intensity is in a vertical, half the intensity is in a horizontal. But because horizontal is being blocked, you have only vertical propagating. That means you have the intensity only half as before. Okay, so then how about here at 0.3, which is when it goes through the analyzer? Well, think like that. You can either completely block it and have 0.2 over there, right? So 0.2 have 0 intensity. That means, if the direction of the polarizing analyzer axis is perpendicular to the polarized light, you can completely block it. But you can also have it where it's a little bit, at an angle. So for example, if you have a electric field, or the light, vertical light moving, and you have then a polarizer, that when the light goes through the polarizer, so this is the light going through the polarizer, instead of things like this, instead of having axis that is, like this, which is perpendicular to the, polarized vertical light, which will completely block the light. So let's say instead of that, the axes are like this. That means there is this little bit of, right, you can see, right, there's an angle phi, which is between the vertical, polarized light and then the axis of the polarizer. So then in that case, you can calculate intensity by taking the maximum transmitted intensity. That means intensity before, let's say here was 0.1, and this is going to be like 0.2, right? That means intensity at 0.1 times then cosine of this angle phi, and the whole thing basically squared. So that's kind of like this cosine square phi means. That means square of the cosine of that phi, right? So that's why one of the things you can do here is, for example, you can see, right, when polarizing axis is perpendicular, that means phi, let's say if I have this, then phi is 90. Cosine of 90 is 0, so you get 0. That's it, very simple. But what if the cosine, what if this is not perpendicular, but something like this, then phi can be, let's say, 30 degrees or 40 degrees and 50 degrees. Again, that's the transmission axis or polarizing axis with respect to the light, vertical light. Then you plug in and calculate that, and maybe you can get 30%, of the intensity one, or 20% or 15%, and so on and so forth, depending on what you have. All right. One thing we can do here, we can actually polarize the light by reflection. So let's say you have an unpolarized light, you can either totally or partially, let's say polarize it by reflection. It's a little bit difficult because you have to find the right, let's say this, theta, right? We call it Brewster's law, Brewster's angle. So that means you have to, have this, let's say theta p in such way, right, that, when the light is reflected, right, it becomes polarized. But there's an equation that can allow you to do that. That means tangent of that angle theta p equals index of refraction of medium B divided by index of refraction medium A. So you can use that to calculate the Brewster's angle. All right, so let's do an example here then. So with this example, right, we should be able to kind of like see what's going on in this type of, polarizing, example. So you have a beam of unpolarized light. That means here you have a unpolarized light with intensity I naught, passes through a series of ideal polarizing filters with their polarizing axis turned to various angles as shown. Okay, that means, so the polarizing, so this is, let's say, the first one, second one, and then the third one. See, then you can see that you can think of, like, let's say this polarized, unpolarized light is both vertical and horizontal. Okay, let's look at the axis of the first polarizer. You can see, right, it's vertical. Right, it's vertical. That means it says, what is the intensity in terms of I naught, right, original intensity, at points A, B, and C? Okay, now let's look at it. So as light goes through here, see this unpolarized because it has X and Y. As it goes to the first polarizer, what will happen? Well, the horizontal will be black, and you will only have then the vertical. And intensity at point A is then always exactly half of intensity that was before. So that was unpolarized light. So you have, I guess you can write as 0.5 I naught. Okay. Now, as the light goes like this, so let me use a different color for the light. So let's use red. So think like this. So this is the the light, right? So now light is like this. That means when it enters this polarizer, or analyzer, I guess, see, it is vertical. But the axis of the polarizer is such that it's not perpendicular, but 60 degrees with respect to that. Okay, 60 degrees with respect to that. That means the light, if I'm calculating it right, so the light at point B, then I have to use then that previous equation, right, that we call this equation. This is known as Malus's law. I can use this then to calculate intensity after the analyzer. All right, so this means that, intensity at point A, so basically, then times cosine of angle phi squared. I like to usually do it like this. So what we had here, we had 0.5 intensity already, right? And then we have then cosine of 60 degrees squared, all right? And if I do that, I'm gonna get 0.125 I naught. All right. Now, what is then the light as it comes out of the second polarizer? Well, it's gonna have this angle, which means with respect to the normal, this will be 60 degrees. So with respect to the normal, it is 60 degrees. All right, so that will be my light coming out of this polarizer 2. Then it propagates to the polarizer 3. Remember, now the angle for the light as it goes to the polarizer 3 is this guy over here, which is 60 degrees with respect to the normal. So what is then, light at point C? Will there be any light? Well, let's calculate. So intensity at C will be intensity at point B, then cosine of phi squared. Let's call this, let's say, phi 2 over there. This is phi 3. All right, so what is intensity at B? 0.125 I naught. Now, what is phi? That's the important thing. Is phi 60 degrees? Or is phi, this phi 3, right? Is it, 60 degrees or is it 90 degrees? What do you guys think? Well, neither of those. Because phi is the angle that between light and the transmission axis of that polarizer. Well, this polarizer has a horizontal axis and the light has 60 degrees with respect to normal. That means this is the angle between them, which is 30 degrees. Again, the phi here is the angle between the light and the axis of the polarizer. And that means in this case, it's 30 degrees and we square that. And if we calculate that, we're gonna get 0.0938 I naught. So that means roughly 9% of the original intensity. All right, so there will be light, but little under 10% of the original intensity, because that's what we have. That's for part A, wrong problem. Okay, so then part B says, if we remove the middle filter, what will be the light intensity at point C? Okay, so imagine if we didn't have this. That means we technically don't have that. Let's kind of see what we have. That means this is now becomes the second polarizer. See the unpolarizer natural light going to the first polarizer, remember, has a vertical axis. Now it has to go to the polarizer 2, because we don't have this anymore, which has an axis that is horizontal. See, then the light gonna come in as vertical and the axis is horizontal. They are 90 degrees, phi is 90 degrees. What is intensity? 0. That means by removing, polarizer 2, this combination of polarizer 1 and 3, right? Or, let's say, gives you no light at point C. Hopefully you guys were able to follow, right? Again, because first polarizer makes it vertically polarized, and the third polarizer, it has an axis that are horizontal, so then vertical will be then completely absorbed by the horizontal transmission axis. All right. All right, guys, so that's it for chapter 23. And I will be then uploading chapter 24 soon, so you guys have time to study that for the final exam.